Today we are going to solve Leetcode 2305, that is fair distribution of cookies. This is a medium level question, and in this question we are given an array of cookies where cookie I denotes the number of cookies in ith bag. You are also given an integer k that denotes the number of children to distribute all. So we are given an array of cookie bags in which the ith index represents the number of cookie in that bag, and we are given k, which is the number of the childrens among whom we have to distribute these cookie bags. So what we have to do, we have to distribute these cookie bags in such a way so that we can achieve minimum unfairness of all distribution. Now what is minimum unfairness? Minimum unfairness is nothing, it's just a combination of distribution in such a way that the difference between the cookie count that we distributed among children should be lesser. The difference should be minimum one. And how we are going to do that, as we can see in this example, the distribution is 858, which is equivalent to 31, and 20 and 10 is one distribution. So the difference between these two values is 1, and as this is minimum, so this is the minimum unfairness distribution. So we distributed 31 cookies to one kid and 30 cookies to one kid. And also one thing, that we have to give one back to one kid. We are not capable of splitting the number of cookies in a bag and distributing it among kids. So we have to give a complete bag. So if I'm saying cookie at 0th index is 8 and I'm giving that back to kid 1, that means the kid 1 is not going to share those 8 cookies with anyone. The total 8 cookies are of that kid. Okay, so we got this question. So how we can solve this question? As we know that we have to check for all the possible combinations, so we can try this question with backtracking approach. So let's see how we can solve this. I already wrote the algorithm here, which will help us when we will be writing our code. But before that, let's try to check the dry run. So I am saying these are the number of cookies and there are 2 kids. K is 2. So if I'll start from this point, so this is the first case where this will be kid 1 and this will be kid 2, right? So I'm saying give this cookie bag to kid 1. So fine, I'll give it to kid 1. So kid 1 is having 8 right now. Then again this is kid 1 or kid 2. So I'm saying again give this bag of 15 cookies to kid 1. So kid 1's total will be 15 plus 18, that will be 23. So again there will be choices, again kid 1 and kid 2, right? So this will be what? 23 plus 10, so it will become 33. Again I gave this back to kid 1. Again I will proceed, so just assume that this is gone that side. So we are again having kid 1 and kid 2. So now again I am giving this bag as well to kid 1, so it will become what? 53. So right now kid 1 is having 53. Again we are having choice, as we do have some more bags. So this is the last bag, so I will give this as well to this kid, so it will become 61, right? And this is kid 2. This is kid 1. So now I can see I ended up this whole cookie list. Now what I can do, I can store the value of this distribution. So what this distribution will be? This distribution will be somewhat like this. I distributed 61 and 0. So maximum of this distribution is, maximum unfairness is this value, right? So this will be our unfairness count. Unfairness count is equivalent to 61 right now. Now what I will do, I will backtrack. So how I am going to backtrack? Now I am going back. So now I will again go back to this bag, and I said previously I gave this back to 61. Now what I am going to do, I am going to minus this 61 bag and I will be giving it back to kid 2. So what will be the case? 53 and 8, right? This will be the unfairness count. So now our unfairness count previously was 61. Now we have to take the max of these two values, that is 53. So 53 will be the maximum unfairness count at this stage, backtracking path. And what we are going to do, we are going to compare this value with this value and store the minimum, because at the end we have to return the minimum unfairness count. So what we will do, we will simply update our unfairness count and make it 53. Now again I will backtrack, I will go back to this bag where we distributed this bag here, right? This is the step 20. So rather than giving this 20 to K1, I am saying give this 20 to K2. And again I will do what? I will take maximum of these two values, that is 33 and 20. So maximum will be 33. I will again update our unfairness count, keep minimum of these two values, so this will become 33, and we will keep on doing this whole procedure, and at the end we will be having the minimum unfairness count and we will return it as an answer. So this was the whole backtracking approach. So right now it was 33, and at the end we will be having our minimum unfairness count, and that will be equivalent to 31. So we will return it. But now there are few conditions that we have to consider. Now what all are the cases? We are doing extra work. Now there are some places that we are doing extra work. Let's try to understand and cut off those steps. So as we can see, there can be a possibility where there are, suppose, two cookies and 3 kids, right? So now we can see we only have 2 cookie bags and there are 3 kids. So we know that there will always be one kid who won't get a cookie, right? We know that this is a point where proceeding with distribution and checking the possible combination won't ever result in a valid distribution. We know that. So this is the condition that we will be checking every time when we are trying to backtrack and check a possible combination, that if the cookie count is lesser than the kids count of kids among whom we have to distribute the cookie bags, then what we said, don't proceed with this path, because we know at the end of this we won't be getting a valid distribution. That will be an invalid distribution, because we want a valid distribution, and that even with minimum unfairness. That's why we will try to eliminate this condition. So this was the whole explanation of this problem. Now let's jump to coding part, but before that let's try to understand the algorithm even more precisely. As I said before, that this is the comments that I wrote just to make it clear like what we will be doing. So firstly, what we will be doing, this is a backtracking function in which what we are sending I, that is the cookie bag index, and the zero count is the one that we just discussed, that we will be keeping a count of these kids who don't have any cookie, so that we will be knowing if we are having lesser cookies and more kids, then we won't be trying to distribute and check the possible combination. So this is for that. Zero count will maintain the number of kids who are remaining. And after that, what we will do in our DFS or backtracking function, we will firstly check all the breaking conditions, all the endpoint conditions where we have to return. So first condition will be this only: if the remaining count of cookies is lesser than the number of kids, then what we will do, we will return float infinity, which implies that there is no possible distribution in this path. So we will return. Condition can be after distribution of all cookies, if all the cookies are distributed. If all the cookies are distributed, then what we will do, we will simply return the unfairness count, because we are already maintaining the minimum unfairness count. Now what we will do, if these are not the cases, then we will be trying to distribute it. So this was the whole code, this was the whole algorithm. Let's try to code this whole algorithm. So first thing will be the distribution among kids. So we are going to store the distribution of kids in a form of list. So we created a list which is of length k, and we initialized it with 0. Now we are saying n is equivalent to length of cookies, so that we will keep a check whether we are having enough cookies to distribute or not. Now inside this function, inside our backtracking function, as we discussed, the first condition will be n minus I is less than 0 count. 0 count is the number of kids, right? 0 count. So if we have lesser cookies, so what we do, we return float. We return float infinity. And if this is not the case, there can be another case, that is if all the cookies are distributed. Then what we do, we will return max of our distribution. That will be our unfairness count, right? And if these are not the cases, then what is the case? Now we will check for distribution. So as I already wrote, we will be returning answer. So answer will be float of infinity, because we are going to find the minimum answer, right? Minimum count. Now what we will be doing, we will be trying to check for j in range k. Now we will try to distribute these cookies among all the kids. So we are saying if this kid hadn't received any bag yet, and this is this kid's first bag, then what we do, we simply reduce the 0 count. But if this kid had already received a bag of cookie or more than that, then we don't have to reduce the 0 count, because in that case it is somewhat, we are going to get a distribution, right? We are going to get a valid distribution, and the fairness and unfairness can vary, but there is a distribution. But if a kid hadn't received any bag, in that case it is equivalent to 0. So that's why we are checking if this is the first bag, then only reduce the count, else no need. And we'll increase the cookie count for that kid. After that, we will recursively call this function and call this function with increased cookie count. So this will go to next index, next cookie bag, and will also send this 0 count. Okay, fine. This is the part for backtracking. But we know that this is a backtracking solution. So what we will do, we will again make these value as it is, so that when they are going to be used again, so this will not reflect any anomaly. Okay, so this was our whole backtracking function. Now let's try to submit this. We can see our solution is accepted and it's optimal. Now let's see what is the time complexity. Let me clean this board and we will see what is the time complexity. So as we already saw that we are using recursive function, so the time complexity of this function is going to be somewhat, time complexity is going to be big O of k to the power n. Why? because we can see that we are checking n possible depth or n possible combinations for these two kids, the number of kids, right? So if there are 3 kids, there will be one more partition like this, and we will be checking for those 3 kids, and we are checking all the combination for the number of kids. That's why the time complexity is this big O of k to the power n. Now space complexity, if we see, then what will be the space complexity? Please bear with my handwriting. So space complexity, as we use distributed set or the current set as we saw in the code for maintaining the distribution count, here this we are using this of length k, so that will be big O of k, and we are also using this recursive function, so it will be having a recursive call stack, and the size of that recursive call stack will be equivalent to n, as we are making n calls, so that will be big O of n. So the total time complexity will be big O of k plus n. So space complexity will be big O of k plus n, and time complexity will be big O of k to the power n in exponential. So this was the whole explanation and code for this function. I hope you find this video helpful, and if this video was really helpful, then you can like this video, subscribe my channel, and I will soon come up with some more questions. And thanks for watching.